Hi, Sean.
Hello, how are you?
I'm good. Thank you. So, shall we wait for some few minutes more so that we can do it?
Mm, okay, yes, we can wait for a few more minutes.
You have slides to show, or oops, I have some people waiting here. Okay.
I don't have any slide. I can cover just the talk, and
Okay.
then I can share a screen.
Okay, that's
Yeah,
great.
that should be all right. So we can start, shall we?
Yes, Sean, you can go ahead.
All right. Hello, everybody. Welcome to 42991 Advanced Water and Wastewater Treatment. So today, we want to have a lecture block 2. So Dr. Sharaf Puncha, so he will explain what's the wastewater reuse plant design, what's the water quality issue, and then how we can make advance the wastewater treatment process design. So before that, I just want to share with you regarding our early feedback. So we got two comments from you. So one is let me share screen. So this is can you see my slide?
Yes.
It's canvas, right?
Yeah.
Yeah, okay. So one comment from student, he or she want to have an announcement because we usually communicate via emails, but one student, he or she want to have announcement tab. That's the reason why you can see all the history of announcement. So some, I don't know, anybody missed the email from our communication? Because some students told me that they are missing some emails. So that's the reason why the announcement will be much better. So that's what we are trying to do. In the future, we will communicate through email as well as the announcement. So we will post to two channels, so you can follow up and you will never miss our communications. Also, second comment was our collaborative teaching. So block one, we provide the recorded videos and the lecture materials and ask you to study, and I brief what the block one is about, and then how we can study and how you can complete your assignment one. And one student, he or she want to have longer lectures so that they can follow Zoom meeting and then stay in our class, so that it's much more efficient to learn about our advanced water and wastewater. So Dr. Charapunchu, that's why he will spend a lot of time with all of you today. It's block one. So if you have any question, if you have any some kind of more additional information for his lecture, even for today 3 to 4 hours after that, you can also ask him to organize individual Zoom meeting or some other face-to-face meeting method, because now we have a less restriction. So you are very welcome to come and see us in our office. If you feel Zoom is not effective to ask a question or communicate with your lecture note or any other question, please come and see us. You are very welcome to discuss about our lecture related discussion. So that's the two main feedback from you. Thank you for your feedback. Also, if you have any question regarding block one for the last month, also if you have any other comment to improve this subject, so please tell me, or you can send the email. Also, you can anytime come and see us. So that's we can keep communicating. Also, regarding your assignment, so assignment due was the Monday, so just 4 days ago. But still, some of students, they request the extension of the due date. So if possible, submit as soon as possible, because to be fair of all the due date of the assignment, it's better to you can submit as soon as possible. Because in the future, if you need an extension, please give us a very strong justification with the evidence. That will be much better to follow up, and then we can also give you extension. So please, this is our first assignment, so that you want to extend. So I will give you a little bit of flexibility this time, but module 2, Charapunchu, this assignment due is the end of this month. So please make sure you can complete your assignment 2 on time, and then unless otherwise you have a special consideration or really difficult situation to complete, so you can give a justification and provide evidence to extend your assignment 2 as well. So please make sure that don't delay your assignment. Alright, so do you have any question regarding block 1 or any other comments you want to improve? Otherwise, Dr. Charapunchu, he will start his block 2 lecture today.
Hi Sean, Meet here.
Yeah, hi Nick, how are you?
Yeah, I'm good, thanks. How are you?
Okay, thank you. Yeah.
I just wanted to ask you something. So the assignment one is, we I'm sure almost all of us would have submitted. But it was quite overwhelming for us because you see, like it's approximately 7,500 words and 30%, right?
Yeah.
Just wanted to make a request, maybe on behalf of all the people that are in the class, that moving forward from assignment 2 and 3, which are also very big ones, can we collaborate with each other doing the assignment? So like maybe a group assignment or something, because it's really difficult to do it along with three different subjects, and it's a lot of information that we need to include in our assignment. So just a request from my end, if you can.
All right. Thank you for your great question. Yes, some of students they like to have a group assignment, but they want to combine 3 or 5 people to submit one assignment. But some of students still like to have an individual report. So our 42991 Advanced Water and Wastewater, we have experience group assignment as well as individual assignment, and then we found out that individual assignment is more effective and the student more engaged and then more knowledgeable for their assignment. That's the reason why we are currently carrying on this individual report at this moment. Also, as you know, our subject outline clearly mention about individual report rather than group report. That's why it is. At this moment, it's a little bit difficult to change it because already we are clear about the subject outline for every student. They have a very clear assignment objective from this subject. So if we change now, it has to go through a long process. So I cannot say it's possible to make a group report, but you are happy to collaborate with any student. So you can discuss, but you can make your own individual report, and then you can mention about I have collaborated with this student, so that it can be possible. I can consider, okay, 2 students collaborate, but you need to submit individual report. So it doesn't have to be exactly same. It can be partially same for your assignment, but cannot be exactly same from page 1 to last page. So that if possible, yeah, you can collaborate, you can submit partially together with your collaborative student. But if possible, this semester we want to stick, and we want to go individual report. So if any other student, if you want to change the group report, so you can partially collaborate, that's acceptable. But at this moment, we cannot submit as a group report based on our subject outline. So if you have any more suggestion, any other student, if they want to have a group report, so please email me, and then I have to consider for next year or in the future, we need to design our subject outline again.
I have something I need to bring up on that point.
Yeah.
Tanya,
Okay,
sorry to interrupt you. In the assignment submission page, when I was reading it, at the beginning it does say to write the name of group members and their contribution. So assignment 1 page was designed to say that there were more than one student. So I found it a bit confusing. I knew the instructions was clear that it's an individual assignment, but it was quite lengthy. So I thought maybe in previous semesters it was ran as group assignments.
It used to be long time ago. Yes, it was a group assignment. So that's the reason why it was there. But now we like to have individual report because based on our experience, individual report is the best for students. That's the reason why we decide to have individual. So don't confuse. So this you can collaborate. I don't mind. You can collaborate. So you can mention in your report. Partially you discuss with this student, you can make partially similar to your collaborative student report. That's fine as long as you indicate, but otherwise then you're expected to have your own way of discussion, way of your assignment. You can learn much more than group assignment. That's our intention. It doesn't mean you don't collaborate. You can collaborate, but we want you to learn more with your individual report. That's our intention. So is it
Yeah.
clear, Tanya and Nick? Mike?
Yeah, but it's clear now you say that, but the only thing that I had is, like you said that previously it was a group assignment, right? And now you have done it to individual. Then maybe a suggestion moving forward would be just to reduce the report length, because even for other subjects, I have like 40% contribution towards the final assessment, and it's the report is hardly 4,000 words among 5 students. So that's very reasonable given all the things that we have to tackle down during the semester of just 3 months. So yeah, you said you can't do anything for now, but yeah, moving forward it might be helpful to other students.
Okay, I will discuss with our teaching team and then I will consider your comment. Thank you.
Thanks.
Any other questions? Otherwise, yeah, Sharon, I will hand over to Sharon, so he will start with you. Thank you,
Okay.
everybody. Happy Easter.
Thank you, Sean. Thank you. Can you go out from the slide, Sean?
Yeah.
Okay, this one. So, okay, where is my first page going? Okay, anyway, welcome to the log 2, module 2 of advanced water and wastewater. Thank you, Sean, for your sharing those SFS early feedback results. And yeah, so as I just want to add on what Meet was saying about the length of the assignment. So actually, we don't really look at the length of the assignment, whether you have 5,000 words or 7,000 words. So it's nothing that related to that. As long as you can, the quality of the report is good enough. So we look at that. So it's people can add so many things and write a lot of things and then make more pages, but that's not the intention. The intention is a professional report. So report just concise and then whatever is just required. So it's not the length of the report that is important, but the quality of the report is more important. Okay, so okay. So these are the overview of today's presentation. Anyway, before that, I just want to know how many of you gone through the lecture that has been recorded and made available to the in the canvas. So can you just give me a thumbs up if you have, or raise your hand in the from this screen. So if you have gone through all the recorded lectures, just to have an idea. So anybody gone through the lectures? Listen to the lectures, video, recorded lectures. Okay, one. So only, so that means most of you have not gone through the lectures. So any particular, I mean, like even if you have not gone through all the lectures, I have 3 sessions, and there were 4 different videos. And the first, so maybe I can share that so that you are more aware of that. Probably this one. So if you go through this canvas, so you have modules, yeah. I think you should be already familiar with this one. So you have block 2 here. So in the block 2, I have both the slides and the lecture slides and the video lectures. Okay, so in these video lectures, we there are 3 sessions: session 1, 2, and 3. So session 1 has 2 parts, part 1 and part 2. So part 1 talks about the water quality and then and sources, and part 2 about the surface water treatment. Then the section 2 talks about the membrane processes for wastewater treatment and water treatment, and then session 3 about the wastewater treatment. So if you're not, he didn't have time to go through the lecture, so please, I encourage you to go through, because this block was designed in such a way that you listen to the lecture first, and then this is the session where we would want you to clarify whatever you didn't understand, and then have consultation discussion about what we're going to do for the assignments. So I encourage you to do once you go home after this session, and listen to all the recorded lectures, because today and tomorrow is basically the today half day, and actually the next tomorrow half full day is supposed to be in the formal class settings. You're supposed to be attending the lectures. Okay, so we will in today's session, I will just give a overview of the module 2 and then 2A, and then I will be talking about a little bit about the 2B, and the session, the assignment 2 is mostly related to the wastewater treatment. So module 2A and 2B is basically for you to gain enhanced understanding of the water and wastewater treatment, biological process, water quality, and all those sort of things. I think some of them you already learned during your undergrads. So this is just a kind of revision for you I mean, it's just a reflection to reflect and remember whatever you have learned earlier. So it was just meant for that, for session 2A and 2A mostly, and 2B is a little bit on membranes, and assignment is basically about the wastewater treatment. So assignment 2 is basically about wastewater treatment. So that's why I will be covering today more on section module 2C, so that's wastewater treatment, and in particular the conventional activated sludge process and the membrane bioreactor. So then we will talk about the assignment 2, and then we have a consultation and a discussion from there on. So it may, depending on how we are proceeding, we may go beyond 4 p.m. today, but yeah, let's see how things, and if you have any more questions, I'm happy to answer. And then later on we will have a consultation session after 2 weeks, live consultation session, and also I'm happy to organize face-to-face meeting if you want, drop-in sessions that you can anytime come to my office and then ask any questions related to the assignments. Okay. Okay, so the first session 1, session 1, which is 2A, was related to the water quality. So actually the water quality describes the condition of the water, like basically in terms of the physical, that is the appearance, the aesthetic, how the water looks, the chemical aspect, what are some of the compositions present, the compounds, different kinds of dissolved compounds present in water, and what are the biological characteristics of any microorganism present. So these all this describes the quality of the water, and determines the whether the water is fit for various purpose. Okay, so this defines the water quality. So it's also based on the water quality, we also come to know, you can determine whether the water is polluted or not polluted. So we also looked at some of the different sources of pollution, the point source of pollution and the non-point source of pollution. So point source of pollution includes those that you can see and you can determine where at the same location where there's the pollution. So for example, the very good example is the wastewater discharge points, industrial wastewater discharge points. So these are the point source of pollution. But if it's non-point source of pollution, includes those coming from wider area that you cannot really define that it's coming from. So it could be like a runoff from the pavements in the cities, urban stormwater, and then collecting all these chemicals or pollutant that's present in the streets. So that's as a kind of non-point source of pollution. The other good example is the runoff from the agriculture farmlands, where people must have used pesticides, must have used a lot of the fertilizers. So those things maybe during the event of the rain, those things may be washed off, right? And then it comes to the river, and then the water gets polluted. So this source of pollution are called non-point source of pollution. So we also talked about the water cycle. I know the water cycle. So this is a simple one, right? That we have, you must have learned in high school. So the water cycle is actually the natural water cycle. So we have evaporation from the water bodies, forms cloud, condenses, then the rivers form rain, and then it goes back to the river, the charges groundwater, and so forth. So it just continues the natural water cycle. And then, but if nothing is disturbed, so this natural water cycle goes on very perfectly. But as more humans are getting involved, more people are living in the urban areas, more the features of the landscape are changing because of the human settlement. Anthropogenic activity, we call it. So this is because of the human activity. It has a lot of impact on the water quality and the water cycle itself. So this is one of the as a result of the climate change, global warming. And these are some of the global warming is really impacting on the climate. The water cycle is really changing actually. So this is we can see that there are places where there was no rain, used to have a lot of rain, or that the rain is not regular like before. Sometimes it rains too much, sometimes there is no rain, drought for a very long time. So all this is a disturbance to the natural water cycle. Okay, so it's all impact because of the climate change. So water quality is important to identify water concerns and how to address them. So water quality is very critical part of water management. So it is not only at the wastewater treatment plant or water treatment plant that we are concerned about the quality of the water, but it is also overall management of the catchment area. Say the whole area, for example, that so even some of the government or the countries, they have a whole catchment, the water management the plants. So the water quality actually encompasses whole the catchment. So it is critical part of the catchment management, and not only related to the specific like water treatment plant. So this is what we discussed in the session 2A part 1, and also these are some of the characteristics of the water that usually defines, and these are very basic ones. So of course you can have hundreds, thousands of different chemicals, because nowadays, because of the industries, many different types of thousands, actually in fact millions of different compounds are being manufactured every day. New compounds every day are synthesized and commercialized. You can see in the many different types of commercial products, they use very different kinds of chemical compounds. All this at some stage becomes part of the water. Yeah, so it becomes dissolved in water and becomes a part of the contaminants. So, but which means it can have lots and lots of different contaminants present in water. But this basic characteristics form are basically from the public perception, there is like whether physical properties and the chemical properties and some biological properties, as we said. So physical properties includes color, odor, the turbidity, how turbid the water is, whether it looks clean or clear or a little murky. So those sort of appearance that gives indication of water quality. And temperature also impacts the air, also gives the quality of, indicates some quality of water. And so chemical properties include what are some of the chemical compositions present in water, say carbohydrates. So these are organic compounds present in water. So maybe it's when people are using and discharging through, from the kitchen or from the toilet, all these things become as a carbohydrate, right? So fats or grease, this becomes part of and they are pollutants. Pesticide that's coming from the agriculture farms. Phenols, people use it as disinfectants. Proteins, surfactants. So there are so many different types of chemicals that's present. So these are just generic one that so this table shows, okay? And biological properties include all these animals and plant products. It can be in the form of waste or yeah, it's mostly in the form of waste, right? So and also the bacteria, the microorganisms present in that's coming from, especially from, say, for example, from the toilets that's used. The fecal matter. So fecal matter is the food that comes from the waste, the toilets. There's a lot of microorganisms present in that. So it can also contain a lot of virus. So these are some of these are the different properties and characteristics of the water that defines the quality of the water. Okay? And so this this is more of the defining the characteristics, but these are some of the parameters that water quality parameters that is generally used. So pH is one of them, and pH really impacts many things. What's the pH? The water pH in seawater, for example, is 8 to 8.5. Fresh water from between 6.5 and 9. And drinking water should be between 5 and 9, and irrigation water between 4.5 and 9. So pH is quite important parameter in the water quality, because the pH determines what happens within the water. Okay, so under different pH, the different compounds present in the water behaves differently. So this is why the pH is quite important, and even during the treatment process, pH of water is very important, because it impacts the treatment processes. For some treatment processes, they are more effective in a certain range of the pH, and if the incoming water source is not within that pH range, then the treatment quality, the treatment process will be impacted. So then you have to adjust the pH so that it is within the range that it can be treated. So hardness is another one. Hardness is the presence of especially this calcium and magnesium in the water. So what happens is, if more amount of calcium and magnesium is present in water, then you'll see that the water taste is also different. And also, especially what happens is that when you cannot even use it to lather your soap. So I'm sure some of you must have experienced the hard water. When you try to use soap, the bubbles will hardly form. So this is in fact the indication that water is hard. And also that water hardness has other implications to the infrastructure, because hard water will form scaling, like for especially the gypsum. So if there's a lot of calcium and then it's also sulfate in it, what can happen is the calcium sulfate can form precipitate and form scales in the pipelines and reduce the pipelines. Also can lead to corrosion and those sort of things. Okay. And total dissolved solid is basically how much dissolved ions or dissolved salts are present in it. So this also is indication if very high TDS, means we call it TDS. If there are a lot of salt present in water, then this also indicates the water is not suitable for drinking. For example, if it's very high salinity, seawater is very high salinity. Groundwater usually also have high salinity. So if it's within certain range of the salinity, say for example, usually anything about 1,000 ppm, is 1000 milligram per liter of salt, is not suitable for drinking. 1 gram of salt. If 1 gram of salt is present in the 1 liter of water, then it is not actually fit for drinking. Usually it can be okay for, say, use in a cattle farm or something like that, but not really for drinking. So usually the WHO recommended one is usually less than 300 or 500 milligram per liter. Okay. And temperature also really impacts, because temperature impacts the many things in the water quality. Say, for example, it also impacts pH. It also increases the total dissolved solid, because some salt which is not dissolved at higher temperature, they will dissolve. At a higher temperature, pH can change, and so many things can. And at higher temperature, the oxygen dissolved in water can also be different. So all this can have significant impact. So what temperature is one of the parameters that impacts actually everything in the water quality parameters. And dissolved oxygen is, of course, is very important parameter, because it indicates the freshness of water, like almost like freshness of the water. Because if this rich in oxygen, that indicates that the water is quite clean. If the total dissolved oxygen is very less, that means that the water is become like almost like a stale water, right? So what it means, like, because if there's less oxygen present in water, that means that there are something in water that is consuming the oxygen in water. Okay, so that indicates. Of course, if this temperature increase, the dissolved oxygen will also be released. So that may also be one way of removing reducing the dissolved oxygen. So BOD, so biological oxygen demand, is actually basically the carbon content in the water, that carbonaceous compound that can be biologically degradable. So this is a measure of actually BOD, means the oxygen demands, the amount of carbon that can be biologically degraded, and how much oxygen is required to degrade that biologically. So that gives the indicator of BOD. So it's basically measures that carbon content that can be biologically degraded in water. So if there are a lot of BOD, that means your water is has a lot of organics, and that means it has to be removed, right? And nutrients. So this refers to especially to nitrogen and phosphorus. Okay. So there are many other nutrients as well, but this nitrogen and phosphorus are the most critical nutrients that defines the water quality parameter, because they have the potential to cause eutrophication. So eutrophication, as you know, is a kind of the depletion of oxygen because of say, for example, if there are very rich nutrients in water because of the discharge from agriculture farm and from the wastewater treatment plant, and if all this accumulate within the, say, for example, even in a freshwater lake or in the running river, what can happen is that under certain very perfect condition, temperature, everything, then suddenly this algal bloom will happen. So like a lot of algae will grow suddenly, and then this algae, once because they grow very fast. When they grow very fast, what can happen is that of course, algae will produce oxygen, but what can happen is when suddenly so much algal bloom happens, they will completely block the water, the sunlight coming to the thing. And then when the sunlight is stopped, then the algae will die. When algae dies, algae is made of organics. And these organics will, then when these organics degrade, then all this biological bacteria that degrades oxygen, organic, say, algae, will suck up all the oxygen present in the water. So that's how you have a lot of fishes dying and aquatic animals dying. Okay. So these are some of the water quality parameters that we have talked in the session video part 1 of 2A. And these are also some of the water quality parameters from the Australian drinking water standards. Okay, so you have a certain range that guidance said that it has to be less than this amount of the water quality guidelines, so that it can fit for drinking purposes. Okay. And then we also touched on the various types of water sources. Okay, water sources that includes groundwater, surface water, storm water, seawater, brackish water, raw wastewater, and treated wastewater. So groundwater, as you know, of course, is quite usually quite clean because uh, they are they during the event of the rain or any surface water on the land, they just seep and actually they are naturally filtered through the soil layer. So usually in most regions, the groundwater is quite pure, and it can of course depending on the level at which the groundwater is below the ground. So if it is going near to the ground surface, yeah, of course, then in that case the pollution level would be much higher compared to the groundwater, which is very deep, for example, like 200, 300 meters. So those are groundwater maybe quite clean and free from pollution. So this is one of the sources of groundwater. So it's in many parts of the world, groundwater is a very important source of fresh water for drinking and also for agriculture. And surface water is in the form of lakes, rivers, and those sort of things, right? So this is also a very important part of the water sources for various uses, like drinking water. For example, this dam shows the Warringah Dam in Sydney. So this is one of the main sources of drinking water for Sydney region, right? So this is a kind of surface water. So we dam it, tap it, and then we treat it and then use it for various purposes. And stormwater is those, actually the stormwater is those that basically coming from the collection of the, especially in the urban areas, through the pavements and those sort of things that we collected and become part of the stormwater and the storm sewers. Okay, so they become a part of the water that coming through the drains and going to the river system. So this is stormwater, and stormwater can be quite a lot of pollution present in it, because it's basically coming from the urban areas where a lot of cars, traffic is there. People maybe waste, littering or wasting a lot of different kinds of chemicals in the streets. So all this can be collected and become part of the stormwater, and so it can be highly polluted. Seawater, of course, you know, this is the seawater is really abundant, and if you look at the earth is very rich with water. This is what we always say, that the earth is very rich water, planet with very rich water, right? Say we say that more than 2/3 of the earth's surface is covered by actually water. But all this water actually is in the form of seawater. So we can't use seawater because this has very high salt content. It's ranging from 35,000 milligram per liter, that is 35 grams, to 40 grams per liter. So it is very high salinity, and then we can't really drink. But now we have a technology to really convert this seawater into drinking water. So you must have heard, you will be, of course, later on doing, Sean will be covering in the last part, desalination. So this is the seawater, converting seawater into drinking water is actually done through a desalination process. The technologies are really developed these days, membrane processes, and then so we have at Cornell one of the largest desalination plant in Australia. So of course, last year it was operated for a few times, few months I think, and then of course we didn't have to really operate because we have enough water now in Warringah Dam. And of course then, you know, because of the technology, availability of the technology, and the water cost of the treatment cost has really gone down. So it's in many parts of the world, in some countries, they just depend on the seawater, especially in the Middle Eastern countries. You'll see that their main source of drinking water is the seawater desalination. Okay, and brackish water is basically like mostly the groundwater actually. So groundwater being present underground and it's in contact with different types of minerals, they can be sometimes quite salty. So you'll see that in some part of the Australia, groundwater is very salty, like even much saltier than the seawater. So it can vary. Some are very directly potable, like low salinity, but some can range more than what is allowed for drinking purposes, and then in that way you have to do brackish water desalination. Raw wastewater is the raw wastewater. It can be from the domestic wastewater treatment plant, or it can be from the industrial wastewater treatment plant. So these are the wastewater sources, the various sources that we can define after they are really highly polluted. So they'll have to be treated before they are discharged or used for any other purposes. And of course, we will talk more this later in the sections. And the treated water is, of course, treated wastewater is one of the sources for various uses as well. Okay, so for example, a very good example is in the Central Park, just in front of UTS. We have the Central Park has a wastewater recycling plant. So all the wastewater is coming from the toilets, the kitchens, bathrooms, everyone from the Central Park building. They are collected in the basement, and they are treated to a very high quality, and they are supplied back to the apartments and use it for toilet flushing, for laundry, for irrigation of those green walls, and also for the cooling towers. So in that way, they can significantly reduce the amount of fresh water required from the Sydney water. Okay, so because they just recycle the same water and keep using it again and again, because the technology is there to treat the water quality, because it's not for drinking purpose, of course, so it's for non-potable purpose only. So to that extent, we have already water reuse experience here in just in front of UTS. Okay, so we also looked at some of the characteristics of domestic wastewater here. So this and domestic wastewater is, it can be wide range of constituents, weak, medium, strong. So so these are some of the characteristics. You'll see BOD, say 300 milligram per liter for a very strong wastewater, domestic wastewater. So it can be the chemical oxygen demand can be as high as 1000 milligram per liter. Okay, so these are some of the. So and you'll see that the fecal coliform here. This is actually fecal coliform describes the microorganism present in water, right? So it's bacterial contamination. So you will see that the strong one has quite high, even 10 to the power 9. So that's a billion counts, okay, billion numbers of total coliform in just 100 ml of water. So these are some of the characteristics. So when you look at that, the water characteristic, this kind of parameters, then you can immediately say, based on the concentration here, okay, this water could be this from these sources, something like that. Okay, so for example, fresh water could be very low in BOD, BOD and COD, and suspended solids. But the total dissolved solids may be high or low depending on the sources. Okay, so just to summarize from the part 1 of the video in 2A lectures, we just have understanding of the quality of the water quality that helps to clearly identify the water concerns and how we address them. Okay, basically the understanding the water quality is quite important to identify what are the concerns of this water and how we address them. Okay, for especially in terms of treatment, and it's a very critical part of managing the water in the catchments and the treatment processes. So there are water guidelines, say Australian drinking water guidelines. These are some of the guidelines. In many countries have their own guidelines in place, and mostly refers to the World Health Organization guidelines, WHO, which is like a mother of all the guidelines. Okay, so they used mostly from the WHO guidelines that clearly shows what should be the quality of the water, if it is for drinking or for different purposes. So as you say, the human activities are one of the main primary sources of changes in the quality of the water, and also that we also talked about the various sources of water with different kinds of water quality. Okay, so any questions so far from this section? Okay, so you can stop anytime when I'm speaking and then just ask questions. Of course, this is just, we're just revising, a kind of revision actually, okay? So let's talk about the bit of surface water treatment. I think I have to little bit brush, it's a bit, so you can really identify, identify from, but just by looking at the wastewater characteristics, which is water and water, fresh water. So the total water is actually a kind of surface water and the wastewater, okay? And the sources can be like stream, rivers, lakes. These are the sources, and the wastewater can be the sewage water, that's coming domestic sewage, industrial wastewater, stormwater, agriculture wastewater, those sort of things. And why treatment is required is basically to remove all the contaminants that's present in water, and the treatment goal for the surface water is basically to make it potable, make it fit for drinking purposes, and to remove all this, not only the pollutant, but also to remove those unpleasant appearance, taste, and those sort of things, odor. Some of this may not be very critical to health, but it still is not very pleasant for drinking, right? So this is why the treatment is required. So water treatment is basically for making it fit for potable purpose and safe to drink. But the wastewater treatment is basically to remove all the pollutants that's present. So many sorts of different pollutants. Especially when you talk about the wastewater, it is the biological oxygen demand, or COD, so suspended solid. This is basically part of the organic matter that is present. So this has to be reduced. And basically the treatment goal is to prevent or to reduce the environmental pollution, and it's required by also the law, legislation, that you cannot release the wastewater until it is treated to certain standard. Okay, so to meet this environmental obligations, or environmental legislation, the wastewater treatment is also required. In some cases, treatment can be further advanced. Advanced treatment is applied because in order to use the water for various purposes. Okay, so if they want to reuse the water for various purposes, other reuses, then they are having a different kind of additional treatment as well. So we know there are three different main processes for water and wastewater treatment: physical process, chemical process, and biological process. These are the three main categorization of the treatment processes. So physical treatment basically involves physical forces, to applying physical forces to remove the contaminants from water. So these examples would include screening, mixing, flocculation, flotation, filtration, sedimentation, etc. So these are all based on the physical forces. For example, sedimentation is based on the gravitational forces, because you are letting the gravity settle the particles. And chemical processes actually involve use of chemicals, or the conversion of one form of pollutants to the other, so that it can be easily removed. Okay, so it could be like a coagulation, precipitation, absorption, oxidation, disinfection, decomposition. So when these certain chemicals are added, so the pollutants present in the water binds with chemically with them, and it changes its the physical property or chemical property, and then it can be removed. So these are the chemical processes. And biological processes actually depend on the target for biological process is actually basically the organic matter. So organic matter is a source of food for the microorganism. So we have a lot of bacteria actually. That actually bacteria, we sometimes it's quite humble, but most of the bacteria, the millions of bacteria that we encounter, is also very, very useful bacteria. So they are like cleaners of the of the environment. So without bacteria, you can't imagine how the world would be. We would have piles and piles of waste, right? So these are the bacteria is responsible for degrading and decomposing all the waste there. So biological process depends on the microorganisms to degrade and then convert into various forms. So it can be in the form of energy, it can be on the form of gases and multiplication of cells, and in that way we can remove the organic pollutants from the wastewater. So this is a typical water cycle of domestic water we use, domestic water that we use. So we have a source here, and then this is the way we apply it. We say user here. So when you get the fresh source, say surface water from river here, so we treat the water through different stages, various stages, okay? And then we finally, with treated water, then we supply it to the household, then we use it here for various purposes, and then we discharge as wastewater. And then again, we treat this wastewater and then discharge back to the river. So this completes the water cycle in domestic wastewater use. But sometimes what we do is we are here actually closing the loop in the environment, but we are not. That sounds a little bit because then you have to again we throw it here again we treat and then again. So it's in both the process a lot of energy is consumed. So now what we are trying to do is to reduce because nowadays, because of the climate change, also because of the increase in the population, the amount of water available here as a freshwater source is also dwindling and it's reducing. So there's not much fresh water left. So what is the option? The option is to reduce whatever we have reused here. Whatever we use, we can reuse it. So what we do is we further treat this wastewater instead of just discharging back to the environment, and further treat advanced treatment, and then reuse for various non-potable purposes. We have actually, in fact, the technology to even treat the water to the even better quality that you would get over here from the with the surface water treatment. You can treat this wastewater to the quality of even better than the fresh water that you get in the tap at home. But of course, still we have this. You have learned in the block 1 what are some of these challenges the people not able to accept drinking water from the treated wastewater. So this is the surface surface water treatment train. It's a little bit different from the wastewater that you will know later, because surface water treatment train doesn't have involved organic treatment, biological treatment. Sorry. So biological treatment is mostly associated with the wastewater treatment. So you have raw water, say surface water coming from maybe from lakes or rivers, and then they are subjected to bar screen that removes large size objects. And then you have a grit chamber that will remove high density, the inner particles, like maybe sand particles or those sort of silt and maybe eggshells, bone chips, those sort of things. It will remove, because if they are not removed, then it can be problematic for the downstream part of the wastewater water treatment, like the pumps. It can wear out the pumps easily, and also it can cause problem in the biological degradation as well. And then we have, this will be followed by rapid mixing. So usually heavy particles are already removed, larger particles removed by this bar screen and the grit chamber. They are usually called as pre-treatment, and then rapid mixing coagulation. So here, usually surface water has a lot of suspended solids, okay, high concentration of suspended solids, because they are flowing through this open surface, and so that they in the process, because when it rains, the storm water from the streams and all this will collected in the rivers, and then they can accumulate, right? So this is what we need to. We'll have a lot of high suspended solid. So this needs to be removed, but they cannot be just simply removed by this grit chamber and the bar screen. So, but one way is to let it settle. Okay, let it settle. Sedimentation, but let the natural sedimentation takes place. But some particle suspended solids is very, very fine. It will take many days to settle. So which means if you want to treat millions of liters of water per day, you require huge volume of sedimentation tank. So you don't want that to happen because the cost will be very, very high, right? So that's why you want to treat in a small area and quite faster. So that's why you have to add this, what we call the coagulant or flocculant. So it's kind of chemicals that you add in water, they rapidly mix, and once it's rapidly mixed, and then they will form a flock, because suspended solid is the very fine particles that not settle. Yeah. So when these chemicals are added, they destabilize, they agglomerate, they form flock, and they become larger particles, and then they will become heavier, and then they settle. Okay, so this is how most of the surface water treatment plant or drinking water treatment plant, they have this rapid coagulation and flocculation. So coagulation is rapid mixing and let the chemicals coagulate with the suspended particles, and flocculation is slowly mixing and then try to make it larger particles and settle, and they will be removed from the system. And still there will be a little bit of flock particles which is not removed by sedimentation, is still not able to settle properly, and this will be removed by further treatment which calls sedimentation here, and sedimentation and then filtration. Let it settle, and then we have filtration, like especially sand filtration is very widely used for surface water treatment. So this will remove all the suspended particles that is formed in the form of suspended sludge. And then this will be followed by the disinfection. So basically to kill all the microorganisms present in the water. Okay, so of course some microorganisms may not be that harmful even if you drink, because this can be useful bacteria, but some can be harmful. Okay, say E. coli and so Giardia and those sort of things. There are a lot of these microorganisms in water that can cause health problems. So this has to be deactivated or killed. So this disinfection, usually addition of chlorine is widely adopted to disinfect the water. Okay, so that's how finally you get the potable water, okay, for drinking purposes. So this one will describes how the surface water treatment is achieved. So you have here surface water bar screen, right? And this will prevent all those fish and larger particles from coming. So you have some chemicals adding here, and then this will be, so it's even pH adjustment can be done here. You have rapid mixing here, and then slow mixing here to have so we have coagulation here, then you have flocculation here, and then let it settle. Whatever settle sludge will be removed, and whatever cannot be settled, they will further filter by sand filtration, and then you get a very clean water for supply to the household. Okay, so this is the process diagram for a typical typical surface water treatment plant. So these are also, there are various treatment trains that you can have. Say if the water quality is very fine, okay, very good quality water, and you don't have, especially like groundwater, or even very a lake is undisturbed, or stream water coming like from a very undisturbed place. So then the water quality may be very high. So in that case, you don't have, maybe even you don't record treatment. So just a simple disinfection is enough to disinfect the water and then supply it for drinking. But if you can have sometimes just a sand filtration. So add chlorine here to kill any bacteria that you may have in the water, and then use some simple sand filtration and then apply it for uses. In many countries also, when water quality is quite good, they use just basic sand filtration and chlorine distribution and then supply it to the houses. And inline filtration includes like so you coagulant, that chemical that will form flow, you can just add here without having any mix. You can have a mixing, but you don't have to have this separate. Say for example, earlier we have here where flash and rapid mixing and the coagulation, right? So you don't have to have that kind of thing. You just inline coagulation. You just put the chemical coagulant here, and then that will go to the filtration, and then it will remove. It becomes safe water to drink. And direct filtration will involve here addition of coagulant, rapid mixing, and then followed by sand filtration. So by sand filtration, okay. And but conventional treatment, that's what I have earlier shown you. So this is usually most surface treatment are associated with, especially if they have a high turbid water as the surface water. So in some countries, the water is quite brownish because they have a lot of silt in it and a lot of suspended particles. So those, in this case, this kind of conventional treatment is must. Like you add a coagulant, you have rapid mixing, then you have okay, so you have okay, so okay, here. So you have just hold on. I will have some slide, just hold on. So anyway, so this involves sedimentation step, which is then we have sedimentation, coagulation, then we have rapid mixing, and then this is followed by coagulation, and then sedimentation, and then the sedimentation is followed by the filtration, and then again chlorination, or final disinfection before it's supplied. So this is the kind of a conventional complete surface water treatment train. Okay, so this ends the module 2A, and then we will now start with the module 2B. We will continue for another 30 minutes. At 2:30 we can have a short break, and then we will continue with the other one. Okay, so let's continue with the membrane process here. Hopefully I can finish this one. So membrane process. So nowadays membrane process has become one of the most widely used the process for various kind of treatment processes. Okay, so we can okay, so any okay, somebody is trying to Fakar?
Yes.
Okay, you're. Can you pronounce? Okay, thank you. So membrane process is becoming very versatile these days, because there are wide varieties, as I say, in the industrial chemical processes where many types of pollutants are produced. So you can find membrane process everywhere. Okay, so membrane process is basically a physical separation process. It's a kind of filter. It's kind of filter, but except in the sand filtration we use sand granules to filter the water, but in membranes we use synthetic the polymer membranes, a very thin one. So sand filters are usually very thick, like few meters, but here in membranes they are just few microns thick, like maybe it's just 150 to 300 micrometers or something like that. So they're very, very thin membranes made of polymers. So these are becoming very widely used in many industrial processes, okay, including the water treatment, wastewater treatment, and also in gas separation as well. Okay, so and it use a semi-permeable membrane, means basically it allows some kind of some particles to go through and doesn't allow the others to pass. So for example, it could be, if we talk about the wastewater or the surface water, the water will pass through the membrane, but it will retain, or it will block the pollutants from passing through. So in that way you can separate. So, okay, and there are different mechanisms involved how it is separated. Okay, so it's physical separation, we call it size exclusion. If the particle, because water molecules is the smallest, water molecule is the smallest particle in the wastewater or the surface water, right? So, and anything that is dissolved, or it should be larger than the water molecules. So all these things can be depending on the pore size of the membranes. It can be larger pores, larger particles, say suspended particles, for example. Suspended particles can be quite like maybe a few micrometers, right? So those sort of things can be easily excluded by the membrane. Okay, so we call it size exclusion. And also there could be other mechanisms involved. So we call it electrostatic expulsion. So sometimes the membranes are charged. Okay, when they're present in water, they are charged. They form a surface, charged surface on the membrane. So it's usually negatively charged surface. So when it's negatively charged surface, anything negative pollutants, any pollutant that's coming into the surface that has negative charge, they will be repelled. So electrostatic repulsion is one of way of separation. Okay, and sometimes it can be absorption. It can be absorbed on the membrane surface and also removed. So these are different mechanisms involved. So membrane is actually process is advanced form of water and wastewater treatment, and it's because of their versatility, because they can be tailored to remove a wide variety of contaminants. They are able to remove any sort of problematic compounds that's present in the water. Okay, so they are really versatile and very effective also for disinfection, because they say, for example, removal of parasites and any microorganism, including virus. Virus is also the bacteria is quite large, but compared to bacteria, the virus is very small. So even the virus can be removed using these membranes. Okay, so to that extent that the membrane is very effective in disinfection. So disinfection basically involves removing the microorganisms, right, from the water, and then it becomes but either way of doing is that the normal I usually do is you add chemicals like the chlorine. So that chlorine will kill the bacteria. Ozone also we use it to kill the bacteria. So, but also membrane can substitute those depending on, of course, the size of the membrane pores. Okay, so this is some of the membrane thing. Okay, so there, as I said, there are different types of membranes, classification of membranes. So there are four majors that we talk about. Will be microfiltration, which is the largest pore size. The smaller pore size than that we call it ultrafiltration. Then comes much smaller is the nanofiltration, and reverse osmosis is the smallest, the very tightest membrane. Okay, so reverse osmosis is the one that which used for seawater desalination, that to remove ions, because ions is like a even smaller than molecules. Right? Molecule is a formation of combination of two or chemicals, right? Two or three different elements, whereas the ions can be just single element, right? So it can remove to that extent. Okay, and the reverse osmosis. This is what we use for desalination of seawater. So depending on here, you can hear from this diagram, you can see how depending on the size here. Okay, the larger size can be removed by MF, smaller size by UF again, and the further smaller size can be used by NF, and the smallest RO will be used to remove. Okay? So you can have the range of sizes, the pore size, the pore size of the membrane. So microfiltration is usually between 100 nanometer and 0.1 micrometer. So 0.1 micrometer, eh? So 0.1 micrometer is 100 nanometer. Sorry. So yeah, so it can be up to 0.4 micrometer also. So microfiltration. So ultrafiltration is between 2 and 50 nanometers, and 2 to 5 nanometer is nanofiltration membrane, and reverse osmosis is less than 1 nanometer. So imagine 1 nanometer is 10 to the power negative 9 meters, I think. So to that extent, very. So usually that's why the nanofiltration membranes and reverse osmosis membranes are considered as a non-porous membranes. If you look at through the technology that we have, microscope, you can't see the pores. You can't see the pores. But if you study the cross section of microfiltration, ultrafiltration, you can see, especially microfiltration, you can clearly see the pore size. Okay. And there are some other emerging membrane processes, like a forward osmosis membrane, that is based on the natural process of osmosis. That nowadays we we are trying to engineer the natural osmotic process that is present in all the living cells, our living cells, all the animals, the cells that we talked about, biological cells. Everything has a membrane. That cell membrane regulates the flow of water and the ions through the membrane. So based on that concept, we also try to engineer that to not only treat the water but also to generate energy. Okay, so this is some of the emerging technologies being developed. So our group is also working, Sean and myself, we are working really on forward osmosis membranes and the membrane distillation. So membrane distillation is another one. For example, distillation, as you know, is a really normal process, right? We heat the water, boil it, evaporate, we condense the steam and to produce clean water. So that's one way of doing, converting seawater into fresh water. But that consumes a huge amount of energy because water has to be boiled, otherwise water will, the rate of evaporation will be very low. And you have to heat up to 100 degrees Celsius. But in membrane distillation is a combination of both heating and the membranes, okay? So you don't have to heat water to 100 degrees Celsius. You can heat up to 40 to 50, 60 degrees Celsius. And then you use what we call a hydrophobic membrane with a very large pore size, equal to like this microfiltration. If you put that microfiltration, normal microfiltration, the water will just pass through. But when you make the microfiltration so hydrophobic, that means water repellent, the water doesn't pass through, okay? Liquid water doesn't pass through. But because of that, the temperature gradient will be created if hot water is on the one side of the membrane and water doesn't go through because it's a hydrophobic membrane. Then what can happen is because of temperature difference, water can easily evaporate from there. And that evaporated water you can condense, and then you can get fresh water. So this is the concept of membrane distillation. So these are also some of the different sizes that the membrane can remove. Okay, different sizes here. So dissolved solids, for example, the compounds like sodium chloride, magnesium chloride, all those sort of things come within dissolved salts. They're within the range of these 0.001 to 0.01 nanometer. Okay, so these are dissolved solids. Virus can be within that 0.01 to 0.1 nanometer. And we have some organics, color, and those sort of things within this range. Bacteria is within 1 to 100 micrometer. Algae is also within 1 to 150 or 500 micrometer. And so these are different sizes of the pollutants that you can encounter in the water. Okay, so within that range, it is how you have to choose which type of membrane is suitable for separation. So if you look at the reverse osmosis here, it can remove majority of the compound. Whatever below this will all be removed by reverse osmosis. So nanofiltration is slightly less, I would say, not that effective as reverse osmosis. Ultrafiltration least, even more less, and microfiltration is the least, that it can only larger particles it can remove. Okay, and conventional filtration, sand filtration, granular media filter will be able to remove only between like around 5 to above 5 micrometer. So anything less than that, you have to use other form of treatment process. Okay. So membrane process has been used for surface water treatment, for drinking water treatment. Okay. As I said earlier, usually majority of the surface water treatment involve this conventional treatment process where there's after pre-treatment you have rapid mixing to add where coagulant is added, then you have flocculation, then you have sedimentation, and then you have sand filtration, and then you disinfect and then supply water, right? But this can be replaced by the membrane also. So of course, depending on the quality of the surface water sources, and also the economics. Yeah, if some countries are able to afford, so of course they can, because they have many other advantages with the membrane process. Okay, so for example, we have raw water here. If you use the membrane, you don't need all the sedimentation, coagulation, everything. So you can just have pre-screen directly supplied to the microfiltration or ultrafiltration, and if it is still you require water for the treatment, you can use even RO, and then you can use it treatment, okay, and then for distribution, okay, or you can use even nanofiltration instead of RO, and then you can use for drinking water. But sometimes, depending on the water quality, even you can just use MF membrane to just get the water, because this UF and MF can almost replace the conventional surface water treatment, because the quality of water that you're getting from ultrafiltration will be better than the quality of water that you get from the surface water treatment. So that is and also later on you will see that the size of the treatment plant will also be very small. I mean, the area required for the treatment plant will also be very small when we use the membrane. For example, if you look at so I don't have the pictures here, but if you look at just Google and look at the surface water treatment plant, you will see a lot of big water, the sedimentation tanks, and there's big filtration tanks. So these all things can be avoided if you can use this membrane, because membranes they can work even on vertical. They can increase the size based on the vertical direction also. So not only just the large surface area required. So the footprint can be significantly reduced. Okay. So some of the key terms that we use for membrane processes are, say, we call this a cross-flow membrane filtration, and there's also a dead end filtration, where if the water that you put in, everything has to be filtered, so everything has to come out from there. So that's called dead end filtration. But cross-flow filtration means whatever comes in, not all 100% will be treated. Some will be removed as a very dirty water, also reject. Okay, and then you get permeate water. So this kind of, we call it cross-flow configuration. So you have a membrane here like this. Okay, so this is the membrane model, for example. So you have a membrane here. So you feed water, so it can be anything. Yeah. So you put water with, say, the QF is the inlet flow, okay, feed water we call, and CF is any contaminant in the water, okay, the contaminant in the feed water, concentration of contaminant in the feed water, okay. So this is the permeate will be the water that's being treated, okay. So permeate water means the water that is treated, okay, pure water. So let's say QP is the flow rate of the permeate water, whereas QF is the inflow, that's it, feed inflow. And CP is the contaminant present in the permeate water. And you have also has concentrate. We have also the reject is called also concentrate. And sometimes it depending on if it is seawater. So for example, if seawater is half the seawater is become treated and then becomes a fresh water, the other half becomes concentrate, because all the salts will be rejected and then becomes a more concentrated. We call it brine here. So QR is the brine flow rate and CR is the brine concentration. So you can have mass balance here. So whatever you come here, whatever you get feed inflow rate has to be equal to this permeate flow rate plus the reject flow rate. Yeah. So you can have a mass balance. You can have a mass balance of the flow, volumetric mass balance, and you can also have a mass balance of the solid concentration or contaminant. Say for example, if it is seawater and you're talking about the dissolved solids. Okay, total dissolved solids. So CF is the concentration of dissolved solids. Then the total coming in the total mass of the dissolved solids coming in here will be the flow rate multiplied by concentration here, right? So that should be equal to whatever is going out as a permeate, and the mass of the contaminants going as with the permeate between water, and also plus the mass that is going as a reject. So that should be equal. So this is the solid mass balance. So based on that, you can also work out the various the process parameters, other parameters, as you will see later on. Okay. So for Q will volumetric flow rate meter cube per hour or meter cube per day, whatever, and concentration will be in the form of, say, milligram per liter, kg per meter cube, and those sort of things. Okay. So water flux is one of the important parameters that we usually use for membrane process. So it basically measures the amount of water that you get as a permeate per meter square. Okay, per meter square. So if you have 1 square meter of membrane area, and if you apply certain pressure, and you get, say for example, 10 liters of pure water, so the flux is 10 liters of water per meter square of area, membrane area. Yeah, so, and per hour, 1 hour. So this is what we call a flux. So flux is basically measurement volume divided by area into time. Okay, volume is the volume of permeate that you get here. Okay, and the area is the membrane area, and T is the time, how the operation, how long you have operated, say, which is 1 hour, right? So then QP is actually, QP is nothing but say B by T, yeah, volume divided by time is nothing but flow rate, right? Volume divided by time, meter cube per second, meter cube per day. So B by T you can replace by QP because it's for the permeate, and by area. So water flux becomes B by AT, or equal to QP, the permeate flow rate, divided by the area of the membrane that you have. Okay. So it is, the unit is liters, liters per meter square per hour, or we also call it usually as LMH, liters per meter square per hour. Okay, in the United States they use GFT, so gallons per square foot per day. Okay, so you can use different, but SI unit we use on the LMH. Okay, and okay, so D will be in the meter cube or liter, membrane is in terms of meter square, and the T is in terms of hour. Actually, LMH is not really the SI unit, of course, because liters, but it's meter cube something per meter square per hour can be in terms of SI unit. So a rejection rate is another, the key terms in the membrane process. Is defines the rate of removal of the contaminant. So for example, you have in the feed water, you have CF as a concentration. Say seawater concentration, for example, the total dissolved solid is CF. So if your CP is the permeate, because not 100% of the salt will be rejected by the membrane, even the reverse osmosis, tight reverse osmosis, still like 0.00 something percentage will be still be going through with the permeate. So some concentration will be still there. So if you know the concentration of inlet concentration minus what is the concentration of the permeate, then this ratio gives you the rejection rate. So that defines the rejection rate of the membrane. So which means, for example, we have microfiltration membrane, ultrafiltration. So you have MF, UF, NF, nanofiltration, and reverse osmosis. So you'll see that as the membrane becomes more and more tight, rejection rate will increase. So which means, for example, for microfiltration membrane, if you talk about the salt, TDS, dissolved solid, microfiltration will not remove any dissolved solid. So CF will 0, because that CP, or whatever you have CF here will come as CP here. So which means CF and CP will be same. So this becomes 0, so rejection will be 0. For ultrafiltration may remove like a little bit of, say 10%. So only say if it is, they say 100 is coming in here as a concentration, only 90 will go here. Okay, so which means 100 minus 90 divided by 100 becomes 10%. Okay, so but reverse osmosis membrane will remove. So for example, seawater here, CF concentration may be 35 gram per liter. Okay, 35 gram per liter. But here in the permeate, you can be just 0.1 or 0.2 gram per liter. Okay, so imagine that will give you like a 99 point something percent removal. Okay. So I have some echo here. Okay. So there's another term we call transmission. Transmission is like defines the passage of the solids across the membrane. So basically, if R is the rejection that is being rejected here, whatever goes there is actually the transmission. So 1 minus the rejection becomes the transmission. Okay. And heat recovery rate is another term we often use. Recovery rate means the amount of water that you put in becomes clean water. Okay, so if you put 100 meter cube per day of incoming feed water, and if 50 of them becomes clean water and 50 becomes reject, then your recovery rate is 50%. So because only 50% becomes the clean water. But if your permeate is 60 of 100 here, 60 becomes the clean water and only 40 becomes reject. That means your permeate, the rejection, the recovery rate is 60 by 100 is 60%. Okay. So usually for the dead infiltration, I would say that recovery is 100% because whatever goes in has to come out. But usually for desalination plant, seawater desalination plant, only 50% of this will become as a clean water, okay, the pure water, and rest will become as a brine or reject, okay, concentrate. So the recovery rate here for a reverse osmosis plant, desalination plant, is usually 50%. Okay, so I think we I'll just try to finish this with, I need just another 5 minutes maybe. So these are types of the different types of membrane modules that we have come across. Okay, we have flat sheet membranes. Flat sheet membranes here you will see here. This is the industrial scale fabrication of flat sheet, and this flat sheet will be wound to make a spiral one, what we call a spirally wound, and it's different layers of the thing, and then they make this kind of module. So in one module of this one, for example, the Dow Jones the reverse osmosis membrane module, you can have up to 50 square meter of membrane area. Okay, and up to 50 depending. Say for example, there's just the size, we have different size of course. The 4-inch one here will have something like around 50 square meter. Nowadays even they have 16-inch larger, much larger size, and then they can have even up like 100 or slightly less than 100 square meter of membrane area within small, let's say, very compact. So that this is the advantage of the membrane, because they can be really designed as a very compact one, and then in a very small area you can have thousands of square meter of membrane packed. Okay, so that in that way the treatment efficiency will be much better. So here you can have these spiral one modules will be put into this kind of what you call is this housing. Okay, these are called housing. Okay, you can see those big the pipe tube kind of thing. So all these membrane modules, spiral one modules, will be put inside, and they will be connected into series. Say sometimes this one housing can go up to something like 8 elements together. So we call this is as one element. Okay, and then you can consider this one as one membrane module. Okay, whole thing. So this one, 8 of them will be series together, and then so in that way you can have many series of this housing to make very large treatment plant. Okay, and there's another kind of membrane, hollow fiber membrane. So this kind of tubular kind of thing, but tubular is a little bit bigger in diameter, but you can have very small size diameter. So it's like less than 1 millimeter. So you can have up to 300-400 millimeter size of the membrane, slightly bigger than your here. So we have this what we call hollow fiber membrane. Okay, so imagine you can have thousands, millions of this packed in a very small container. So you can have very high packing density, which means with very small area of membrane. For example, this may have something like a 10 square meter of membrane, very small one, right? A small one, say it's much smaller than the spiral one. It can have even more packing density than this spiral one that we touched earlier. Okay, for say I said that 8 inches and 4-inch diameter, 1 meter length will have around 50 square meter of membrane area. That this one earlier that we talked about. But this one for the same size, for the same volume of that membrane size, you can have probably twice as much membrane area. Okay, with the hollow fiber. So hollow fiber has that kind of advantage. Okay, so and then you can all these modules can be then form an array and then form a large treatment plant. Okay, so even you can have this kind of hollow fiber membrane submerged under the wastewater treatment plant. So we will be talking about the membrane bioreactor. So membrane bioreactor is a form of this hollow fiber membrane. Usually, you can use the flat sheet also, but usually hollow fiber is the most preferred. So you have a hollow fiber membrane, this kind of membrane areas here. You submerge in the wastewater, and then they will just suck the clean water out. Okay, so this is a kind of a membrane bioreactor. So, but they have a lot of problem with the membrane. So it's not that it's very versatile, but still it's a lot of challenging. Fouling is one of the biggest challenges. Fouling means the deposition of all these particles like organics, inorganics, everything. They will see, if you can look at them, the photos here, the membranes become very foul. Like all the microorganisms in organics can be deposited on that. Then when the organics are deposited, microorganisms grow. They can release a lot of slimy things, and then they can really reduce the water flux. We were talking about the water flux, right? The amount of water, volume of water coming per unit area, per unit time, that will be significantly reduced, and then you have to do a lot of cleaning. So this is one of the challenges of the membrane. So fouling can be because of inorganic fouling. It can be also biological fouling, we call biofouling, and organic fouling. Okay, so all this can deposit on the membrane and cause a lot of trouble. So you have to see, if you look at here, the membrane bioreactor, if you take out the membrane, you'll see a lot of deposits here. So those has to be cleaned very often. Okay, so this is one of the challenges of the membrane process. But they are it's natural. You can't really avoid, because when you treat, something has to deposit on that, right? So because we are trying to remove that, and that organic, that pollution that caused water pollution problem is, when filtering, it has to remain somewhere. So that is the challenges of the what we call it membrane fouling. So there are many ways of solving that membrane fouling. We try to backwash the membrane, especially macrofiltration and ultrafiltration. We can do backwashing, but of course we can't do like reverse osmosis and nanofiltration membrane. You can't do backwashing, but then you have to do all this chemical cleaning. Okay, we have acid-base cleaning, acid cleaning, base cleaning, and also we use special kind of commercially available. Some companies formulate certain kind of chemicals to wash specifically the membrane. So those kind of agents, cleaning agents, are used. And sometimes, in order to prevent biofouling, we also try to disinfect the water. Because if there is no bacteria coming in contact with the membrane, then the membrane can last longer and it can prevent biofouling. So in that way, they try to disinfect the water before sending it to the membrane. And there are many other process parameters, process control that you can also adjust to reduce the membrane fouling. So we have some basic membrane calculation here. So we can so we can have a short break now with 8 minutes plus. So can we break for 10 minutes, and we can come back at 2:50? Is it okay, everyone? We'll resume the lecture at 2:50. Now it's almost 2:40, and we'll resume at 2:50. Is it okay? Yeah. So please have coffee or tea or something, and then we can resume.